Okay.
Hello, everyone. Welcome to our points distribution webinar. And before the talk, I would like to make two small announcements. The first one, the next week will be talked by Yeli New, and it will be half an hour area. I'm sorry. I'm sorry. It will be half an hour earlier. It was my neighbor. Half an hour earlier, and also after the talk, we have some time to socialize, like to chat with people. So if you have time and would like to talk with people, so please stay in Zoom. So our today's speaker is Mircea Petrache from Pontificia Universitat Católica de Chile, and he will talk about sharp isometric inequality, discrete PDS, and semi-discrete optimal transport. So please, you can start.
Yeah, thank you. Thank you very much for inviting me here. And I realized that there is no point configuration in the title, but it's about point configuration, actually, the point distributions, the talk. So you will see. Anyway, so the main I start here with some geometric motivation, which is going, so is just a very far view of everything, because the main motivation for me to start the work I'm going to talk to you about was to understand notion of curvature that matter for point distribution. What is correct discrete version of curvature? And the simplest curvature I could think of was mean curvature, but also others would be interesting, but are more complicated. So basically, mean curvature comes in the isoperimetric problem as a byproduct, as the equation of critical points for the area where you fix the volume, right? So if I have a surface, I have being critical point for the area corresponds to having mean curvature 0. And then if I have fix the volume, then the minimizer of the critical points of the area at fixed volume will have constant mean curvature, and you can get that for by this Lagrange multiplier applied in a function space. And so these are constant mean curvature surfaces, right? Sphere cylinders and unduloids in 3D. And so basically, okay, so here we are not going to focus on this differential geometric part, because I don't have anything to say about that problem, but about the minimizing the area at fixed volume, right? And then these are kind of well understood problems in the continuum, but what happens in a discrete world? That's the question. That's the question I am interested in. And the motivation for this question is this minimum energy problems with the very simplified potentials. Okay, so basically this I start with this part of motivation because just to show that the hypothesis to start the setup that where I start with in the problem that the main problem of the talk is really something that can happen, and in some cases is proved to. There are proofs for simplified setups where such so there will be some graph coming up and some discrete point configuration, and these graphs and point configurations are motivated by this this problem. So where I minimize, I have a one well potential, for example, like this, and here it will be, it has a well at distance 1, and for this is like the Lennard-Jones or similar ones, and then you are minimizing this kind of energy among a fixed number of point configurations, and then you find that they form, so all the points want to be at this distance or close to it, close to distance 1, and in fact they do so, and they form a very regular configuration. in this case, a triangular lattice, right? And then there is no proof of this, but there is a proof for not this potential, but rather a simplified one, that a kind of caricature of this that I'm going to show in the next slides. And then this is called the sticky disk problem. And then Toth and Heitman-Radin were studying this and found that actually the best shape that you can have of a large configuration of sticky disks is triangular lattice. And then there are more recent results. Okay, so disk is with K or with C. Both are correct online. It seems that both are correct. Anyway, so there are other results which say that, well, the optimal shape at fixed n is a hexagon, and the worst, the farthest away that you can get from a hexagon is that you are off by a number of points, which is a power 3/4, right? So this is proved in these works for the for this sticky disk problem, but there are other models of square lattices or cubic lattices in 3D, where more recently there have been these n to the 3/4 laws proved. Okay, so there are not only it's rigid, but you can also bound the fluctuations around the optimal shape, yeah, in some simplified models. Okay, so this is about the sticky disk and the kind of caricature potentials. And then there is this paper by Tile of 2006, which is saying that I have my caricature potential. So let me just tell you here, I just move a little bit to the next slide. So the potential is infinity here. It's -1 at 1, and then it's 0, right? So it's a caricature of the one of the Lennard-Jones, right? Because the Lennard-Jones is high here, and this is infinite, and here it's has only one point where it gives -1, and the rest is 0. So this part here, the tail, which give you problems, they also get rid of it, right? So in that way, this is a caricature of the Lennard-Jones. And it's a model of simple one-well potential to see what could be going on. And so in this case, you would think that no point can be a distance larger than closer than 1, and no point can and then you want to have the maximum number of points at distance 1, so that you have a lot of contributions equal to -1. And then you find out that a point can interact with at most 6 points. Otherwise, these neighbors, if you have 7 points, then the neighbor that are a distance 1 to the center, then they will be closer than 1 to each other, and so the potential will be infinite. And then you have this 6 hexagon unique shape, which is the building block of the proof that this is optimal. And then we found without much, this is not much effort to find this other case where you are like you allow distances between 1 and square root of 2, which give contribution of -1, and then in that case you can have at most 8 neighbors for each point, and if each of these 8 neighbors in turn has 8 neighbors at distance between 1 and square root of 2, so that it has the maximum, the minimum energy per point contribution, then if this is true for all the neighbors, then you get that this square here is rigid. Yeah, you have a rigidity of the interaction graph for which have a square shape, and then you have a square lattice rigidity result. Yeah, and then this is also robust. This is also something robust under perturbation in the same way as the Tile result for the triangular lattice. Right? So basically, I besides that I am always excited about this result. The other thing is that I mentioned this so that you can find examples of point configuration and graphs in which later you want to study the optimum shape, which here was a hexagon. For this square lattice problem with bones along the diagonals, you will get an octagon. And in general, there is a kind of predictable way to guess the optimum shape that you will get. Okay. And then, so the question is how to guess it, and when is this crystal shape really the best, and not the best up to small fluctuations, right? When is it precisely best? So this is the discrete isoperimetric problem we talk about in this talk. And so again, basically the proof that I'm going to tell you for sharp and interesting discrete isoperimetric inequality is based on imitating the continuum case proof. So the continuum isoperimetric inequality, the nicest form is this. I try to find this shape, this H. So H would be the best shape, and is the best shape if for all other shapes, this isoperimetric quotient, so I put the area, I put it to the D and the volume to the D minus 1, so that the units of measure cancel, and this doesn't depend, is invariant by rescaling, right? This is the only reason why I put it in this form, right? So I want the isoperimetric quotient for my shape to be the smallest one, okay? Or equivalently, easier to say, but this is maybe it's not you have to fix the scale in order to talk about this other equivalent formulation. H minimizes the perimeter at fixed volume, and it's good to have scale invariant scale invariant quantities if you want to talk about this discrete and continuum cases, because there is always the question, otherwise there is always the question, how do you compare the scale of the lattice or the point configuration that you are looking at with the scale in the continuum that you are trying to imitate? So it's a kind of nicer, it helps a little bit, but is not essential. And then you have other notions. So it's important to have weighted notions of perimeter, right? So where instead of taking just finding the area, integrating the area only, the volume area of the boundary of my set, I also put a weight on the direction, right? So I have a weight, and I ask for this weight to be very close to being a norm. Only the symmetry is not present. So I want it to be positively homogeneous and convex, right? So I have a positively homogeneous convex function that gives me the weight for my normal vectors to the surface. Okay, and then you could also put a weight in the ambient space, say that some parts are weighted more, some parts are weighted less. Usually people have this weight, for example, Gaussian, and this is motivated by dimension reduction kind of results. Anyway, so but for us, we are going to concentrate only without weight in the bulk, only weight on the boundary. And the weight on the boundary is, for example, if I want to imagine that my model is giving me a crystal with facets in some directions, it means that it's cheaper to cut my my atoms or my crystal. Say this is a piece of a crystal. It's cheaper to have an interface in that direction than say in that with its normal direction, right? So it's really useful to have this G in order to model real life crystals. To have, otherwise you are having only the ball as an optimizer if G would be constant. And then the optimizer is kind of the ball of the so what I would call the dual norm to G. Yeah. So H is all the which would be the optimal shape. This was found by Wolf. So this is called the Wolf shape sometimes, but I call it H because, well, in the Lennard-Jones in 2D it's a hexagon, so that's why H. And then so this H is all the points such that when I take the scalar product with any nu, this is smaller than G of nu, right? So it's enough to take nu of norm 1 because anyway G is it's homogeneous, but you can also ask it for all nu, it's equivalent. And then, okay, so to pass from the discrete to the continuum, we have done some work on that with a colleague, Giacomo Del Nin, a postdoc in Warwick, and then we are taking the discrete to continuum limit of the isoperimetric problem, or actually of the minimum perimeter problem. Discrete to continuum limit where you are taking configuration in a crystal or in a quasi-crystal, and take the scale of this crystal to going to 0, right? So in that case, there are many cases in which you can pass to the continuum and get from the discrete to the continuum in this limit. But in this talk, I'm interested at fixed n. So this would be a bit different than that. Anyway, so for the proof of the isoperimetric inequality, right? So the isoperimetric inequality in the continuum means take this h here and prove that this part up here is true, right? This is what I call the isoperimetric inequality in the continuum. For h as below, this wolf shape, the above is true. This is what we are going to try to prove. Okay, so there are two strategies. So here we are going to enter into the proofs. There are two strategies in the continuum case. So the first one is solve a PDE and use convexity. It's interesting. It's kind of magic. Okay, so this is really nice proof. Okay, so basically this is the idea. I think is of Cabret base, and then there are links to previous work of Trudinger. Okay, and Cabret, I think Cabret actually the initial paper I couldn't find it. It's in Catalan. It's in 2008 or 2009. Or but I couldn't read, so I couldn't find that. But I could find this other paper, which is kind of a generalization of the initial work of Cabret. And then, so here, what do? We solve a Neumann boundary value problem. So we have here Laplacian equal to constant of u in a domain omega. And then on the boundary, the normal derivative of u is equal to my weight function g. Okay, so this is a Neumann boundary problem. And you find that this is, if I put a constant, then this constant needs to be pg divided by omega. This just because of the divergence theorem. Yeah. Yeah. Okay, so if this is constant, then this will be actually equal to integral of g of nu because of the boundary value. And this is actually pg of omega. Yeah. And here this must be equal to the value of Laplacian of u, which is constant, times omega. And so the only constant value that I can put here is this, right? And in that case, there exists a solution and is unique up to constant summand of summing a constant. And okay, so for each omega, I keep to myself, I keep in my mind a solution to this problem, a u, and let's go on. And so for a function u, I define its contact set. So the contact set is that I have the graph of u, and then I look at all points in omega, so values of x, such that the gradient of u at x is giving, so the tangent plane to the graph of u as at x is staying below the graph of u over this whole set omega. Yeah, so it's a kind of the points where the tangent planes that stay below the graph are touching my graph. Okay, so this is the PD part, and this is the convex part. And now to get my isoperimetric inequality, one proves that. So to prove that the Wolf shape is optimal, one does like that. First, I prove that the Wolf shape are the gradients at the points of the contact set. So the gradient of u taken at each point of the contact set, this will give me the whole something larger than the Wolf shape, right? And to prove this, one does like that. So to prove that H is contained in the contact set. Let me jump this proof and see why this is important. Okay. So suppose that I know that H is contained in gradient of u of the contact set, then H is smaller than this. The volume of H is smaller than the volume of the set of gradients from the contact set. And suppose u is nice that I can do all my formal manipulation, then I can integrate. This is the integral over of the density 1 over the image of the contact set, and I change variable. I change variable by this map gradient of u. Okay, so the determinant of the Hessian is the Jacobian of the change of variables. But now this Hessian, I can use the arithmetic geometric inequality for its eigenvalues. So the determinant of the Hessian is the product of eigenvalues smaller or equal than the arithmetic mean of the eigenvalues to the d. So the Laplacian, this is the Laplacian of u over d to the d. But the Laplacian of u, if u is my solution, then the Laplacian of u is this pg of omega over omega. And then here I get basically my isoperimetric quotient, right? So I get in the end the result of all this by keeping in mind this d to the d is the d to the d times h is equal to the isoperimetric quotient for omega. Yeah, here I use that the gamma of u is included in omega, so that I get one other inequality, right? And then here I change notation, so here it should be h and g. So due to the duality between h and g, now I can find that pg of h, actually this is the definition of it. And if h is really is the set of x such that x dot nu smaller or equal than g or smaller than g of nu, then when I integrate g of nu over the boundary of h, then I have equality. Yeah, the boundary of h is equal to x dot nu equal to g of nu. Yeah, so this is what I mean by duality, right? So now I have the integral of the boundary of h dot nu, and this is actually by the divergence theorem is the divergence of x, which is d. Yeah, so I get this that pg of h is actually to d times h for this because of the relation between g and h. And then I have that actually this is the same as the isoperimetric quotient for h. Yeah, h to the d minus 1. Yeah, so and then I get my isoperimetric inequality this way. Yeah, so if you see in the proof, what was happening is that I have this claim that h is included in the image of the in the gradients appearing in the contact set, and then I have an arithmetic geometric inequality, right? And then this plus the equation that I have allows me to prove the final inequality. It's kind of magic. I mean, it seems magic, but then if you think about it, there are many connections which one can then justify and say, no, it wasn't magic. Anyway, so why is how to prove finally that h is included in the gradient in the set of gradients of the contact set? Well, if p is a point in h, this is the definition. It's saying that p times nu is smaller than g of nu for all nu in s to the d minus 1, or also all nu in rd. Yeah, because again, g of lambda u, g of lambda nu is equal to lambda g of nu. Using this, it's just equivalent to that. Okay, so anyway, I have this inequality, and now I look in my contact set definition, and this can also be stated as saying that u of y minus a gradient of u at x times y is larger than the same thing with y replaced by x. Okay, so it's in a way it's saying me that I have to look for minimum for the x values, points x, such that u y minus p dot y has a minimum at x. Okay, so I'm looking at that axis, and then I say, can x be in the boundary? It will not be possible. This is because if it is, if this minimum is achieved in the boundary, then here I have a minimum, and then when I go towards the interior of omega, I must grow. Otherwise, it's not a minimum. And then this gives me that if I take the normal derivative across the outside normal, then this is smaller or equal than 0. And this gives me that derivative of nu in the direction nu of u is smaller than p times nu, but due to the fact that p is in H, this is smaller than g of nu. So I have a contradiction because I have that this is smaller than g of nu, but in my equation I was looking for u which satisfies equality, not a strict inequality. So this is a contradiction. So my PDE is just giving me enough kind of version of maximum principle to say that that the minimum for this kind of function can only be achieved in the interior. But if u is smooth, and then I have a smooth in the neighborhood of a point, and then it can have only one point in the subdifferential. So one can find that actually p must be the gradient of u. This is supposing u is smooth. If it's not smooth, you have to do some other tricks to approximate by non-smooth problem by smooth problems. Okay, so p is smooth, and then I have this inequality from above, yeah, because using the fact that x is a minimum of this function, and then I have that p is in the subgradient in the gradient applied to the contact set. Okay, and actually the gradient applied to the contact set is a version of the subdifferential of the function, if you know from convex analysis. Okay, so there is a convex analysis part that gives you some inclusion, and then you have an arithmetic geometric inequality in this proof. Okay, just to have another viewpoint on the same kind of isoperimetric inequality, I go fast towards a second strategy. In a certain way, one could think that maybe Cabret was inspired by this other strategy, and just make a PDE version looking nicer of the same point of view. But I don't know. It's still very useful. The work that from Cabret is just the most useful that I could find. And then okay, so here this is by mass transportation, not optimal mass transportation, but just transportation without optimality necessarily. So here I am looking at a map that is transporting omega to H in the sense that I have here omega, say that I have here H is smaller, doesn't need to have the same volume. And so my T is just moving, is the push forward across T via T of this measure is equal to this other measure, this other density, right? So it's just moving this mass, a mass distributed uniformly in omega, it moves it to a mass distributed uniformly in H. And now other notation. So this is kind of notation in a way. Other notation is kind of a dual, not a dual norm because it's not necessarily a norm, but something that would be a dual norm to G if G would be a norm. So it's something whose unit ball is H. The unit ball, the G star is equal to 1 or smaller or equal to 1 is H. That's kind of the dual norm notation. And then if T is moving omega to H, then G applied to T of X is smaller than or equal to 1 almost everywhere in omega. And now this is it. So now I have this determinant of gradient of T is equal to H over omega. This is coming from the first point because this is the Jacobian of the change of measure. So if T moves one measure to the other, then the determinant of the gradient is equal to H over omega. And here I have something looking really promising for isoperimetric quotient. And now I use again arithmetic geometric inequality here. I have now I have this matrix gradient of T, and I look at the eigenvalues. So I do the product of the eigenvalues is smaller or equal than 1 over D, sum of the eigenvalues to the 1 over D. And so I get here that is bounded by the divergence, and then I apply the divergence theorem. So here I was being precise. I put this is the reduced boundary, but you can forget about it. Suppose everything is very smooth. So then the reduced boundary is equal to the boundary. And then I have T times nu. This is bounded by kind of a version of the, I mean, either convex duality, or you can say that this is the analog of the Cauchy inequality, Cauchy-Schwarz inequality. So T times nu omega is smaller than G star T times G of nu omega, but this is more or equal than 1. And so this is bounded by, forget it, put it equal to 1, and I get integral of G over the boundary, which is the perimeter. Okay, so it's another version of the same. And again, the link is that you can take T is equal to the gradient of U. Okay, so if I have in another problem, I have U, and I solve an equation. Here I can just forget about all this with the equation and just look for some optimal transport map T, or some transport map T. Okay, and then you get the same in the end. If you rearrange terms, you get the same inequality, same isoperimetric inequality as before. And okay, in both these cases, you can then say, well, but what is actually age? I mean, so you can prove this inequality without just by defining age and then applying all the steps. But now you can also prove that equality can only be achieved if omega is equal to age. Yeah. So in both cases, if you look carefully, you can say that omega that equal happens in all steps if and only if age equal to omega. Okay, because why? Because here in order to have this inequality to become equality, you must be that you must have that on the boundary of omega this G star T is always equal to 1, and also the G of nu is always equal to 1. And so I mean, and then here, in order that this is equality, it must be that T times nu is equal to this product. Okay, so I will not enter into the details of this because I want to pass to the discrete case. Okay, but anyway, it's not so hard to find that equality case can only be verified for age equal to omega to find the optimal shape from the optimal shape is unique in a way. Okay, and now what do I want to prove as a discrete analog of this? So I want to prove in the end this kind of inequality which looks similar. You have the cardinality of omega to the d minus 1 bounded by a constant times the cardinality of the boundary to the d. But I want to have a little bit more freedom, and I will put some weights. Okay, so basically what the setup is this. I have a set of points V in the space. This I have V, and then I have some edges between points in V, and this gives me a graph G. And then for each edge I have a weight. Okay, and then I suppose that G of an edge between X and Y is equal to doesn't depend on the order, right? G of X, Y is equal to G of Y, X. Okay, and then so the boundary, I put weight G. So I just sum for all points X, Y in the boundary of omega, I sum the G of X, Y. And this means that, so I look for X in omega and Y outside omega complement. Okay, so this is the directed boundary. Edges directed from inside to outside. It will help a little bit for the notation. So okay, so this is the inequality that I want. And then I want the inequality to be sharp in the sense that the constant C is not 10 millions, but is just the best possible. So it's equality should be achieved by some omega. But actually, I mean, you don't want that this is, so imagine you have a V, I put here a little hexagon, and then I continue with a random configuration, then my best shape maybe is just an hexagon, but is realized just once in my configuration. Well, this is not very interesting. It would be interesting that I have, for my crystal problem, that I have very large crystals that are optimal, right? So it would be nice that it's achieved for infinitely many values of cardinality of omega, so that there are infinitely large omega that satisfies equality in this inequality. But yeah, and now and okay, so basically just a little bit that I give some the main reference for this for me is just Hamamuki in 2014, where he so the goal more or less explicitly stated was that he wanted to find a discrete version of the strategy of Cabret, which is sounded a very nice proof. This proof of by Cabret with the PDE and so on. And so I agree. I also want to generalize to the discrete case this strategy by Cabret. And so basically he did it in the case of the ZD product graph. So the graph where you have nearest neighbors connected in ZD grid, and G is constant. And then you find that the best shape here is a square or a cube or a hypercube, and that the whole proof can be adapted. Okay, I would say that the most difficult part is to adapt the arithmetic geometric inequality to the discrete case. Anyway, so and then with Matias Gomez, who maybe he was in the audience. I don't know. So with a student here in Santiago, in a different university, we were starting to look at this work of Hamamuki and find more general versions of the same strategy, right? So we found actually that not always there exists a sharp inequality. So the simplest case is the triangular lattice. Yeah, so you have you tessellate by equilateral triangles the plane, put equal weights on the edges, and then here the sharp inequality is this. You have this sharp inequality, but it's not of the form that we are looking for, right? So the what is really nice form that is coming in the continuum case naturally, in the discrete case, well, only the leading order. If you look the leading order, this is like gradient, like this boundary of omega squared divided by omega. Cardinality of omega bigger or equal than 3. Yeah, this is the leading order of the equality of the inequality would be this. But and then in fact, if you take omega that tends to the continuum version in a correct way, you really get this limit. So the limit that is an Euclidean, it's a continuum isoperimetric inequality that you expect. But in the discrete, the sharp inequality is more precise and more complicated, and so this is mysterious yet for now. What would be the correct classification of all the inequalities that one could get in the discrete? Okay, but still, this here equality is achieved precisely by all hexagons, all perfect hexagons in the plane. Okay, so this is kind of a hint that situation is more complicated in the discrete case. Then we have many results where we can construct sharp inequalities, right? So we can find the honeycomb graph. So this a graph like in a honeycomb that in this one, the hexagons, so if I take vertices that form a discretized version of a hexagon, then these are optimizing and I have a sharp inequality. Or I can have something else in higher dimension. For example, I take the Voronoi cells of the body center cubic lattice. So these are truncated octagons, something whose faces are hexagons and squares. Yeah, something like that. So the Voronoi cells, I take the Voronoi diagram, and then I take the one skeleton. Just I take the graph that forms the one skeleton of the Voronoi diagram, and then I fill this fills the space. And now I look for the isoperimetric inequality in this graph, and it turns out that the shapes form a rhombic dodecahedron. The optimum shape is a rhombic dodecahedron. You kind of so there is the continuum theory for the Wolf shape that allows you to kind of a little bit guess what would be the correct shape, but that it realizes the discrete the equality in the discrete isoperimetric inequality. This is not always true because of the example of the triangular lattice, right? And anyway, we have a kind of a recipe for constructing this optimum inequalities, which can go on for example, if I have these so-called Coxeter triangulations in more general dimensions, where you have a kind of distribution of hyperplanes that respects a symmetry group. If I have this, then our recipe could, in theory, apply to this, but we didn't enter into the details. Right? So this is a hint that there is a whole class beyond what was known before, which was ZD. Okay, so these are just some sample results to say that there is something that you can say based only on imitating the Cabré and the optimal transport strategies for this problem. So how do we do it? How do we do this discrete result? You have to bear with me for one slide or two. I'm going to fix a little bit some definitions, and then you will find out maybe that these definitions are work together in order to get you a result. Okay. So first of all, I have to introduce something new, right? So you remember, so far we have a graph and a weight v, some edges and a weight on the edges. And then I want to find the finite omega that for all finite omega this inequality is true, and for many omega this equality is achieved. The equality in the inequality is achieved. But now I introduce something more in order to have a Laplacian. So you remember I was solving a PDE. I was having here a Laplacian is equal to, it was PG divided by omega. PG of omega divided by omega in the continuum. But here now I have to decide what Laplacian, what is the correct Laplacian that I want to use. So in one have different notions of discrete Laplacians, and in the Hamamuki case, in the previous case, he was just taking the usual discrete Laplacian in ZD. Yeah, here there is one candidate which you can find by intuition. It's just directly the difference, all the differences of u at the point x and all its neighbors y, and I sum. And more generally, I can put this other definition of a Laplacian, where I have this a squared appearing. Okay, and then I suppose that the edges of my of my graph are where a is different than 0. So I can just sum over all the, here I can sum over all the vertices, because the ones that are not neighbors will be equal to 0. We will have 0 contribution. Okay, so basically I do this kind of Laplacian with matrix a squared given by a squared. Okay, and so my discrete PDE will be replaced by something where you have this. So I have the sum over G applied to the exterior normal discrete vectors, and I divide by the cardinality of omega. But here I can only afford to have an inequality. In general, there is no solution to the case with equality, but only to inequality. Okay, this is so the case if I have an omega that is say that this is my omega, and for some reason I have edges coming from different vertices in the last layer of omega, last layer of vertices sitting in omega, and I have two vertices which are going to have two vertices in omega which have a neighbor outside omega that is in common, like here, like this one. Then if this happens, then it will happen that this system, which is actually if I put here equality, this will be a linear system. It's just a linear system of equations. Then you find that it's overdetermined. Okay, so you find that the case in which if the case with equality, Laplacian a of u equal to something, and this kind of the discrete version of the normal derivative of u is equal to something else. In this case, is g over a. Then this will be Hess solution only if this doesn't happen. if this bad problem doesn't, this coincidence of edges doesn't happen. Otherwise, you see the values of u that I would like to put in the next layer of omega. Here I would like to have two choices of the value of u, not one. So I would like to, it gives me too few values of u to define on the nearest neighbors of omega with respect to the number of edges on the boundary that I have to fix, where I have to fix the value of the change of u on these edges in the boundary. Okay, so you have here to put an inequality, and then you have to put the sign of the inequality correctly so that the rest of the proof will work out, and this is the correct sign. And then I have to, I have three things to think about: the subdifferential of u at x. So are the points in R, these are the points in Rd such that the plane passing through x and with this gradient equal to p is only sitting below the graph of u. This is the subdifferential. And then if I just don't want that this happens for all z in omega bar, yeah, omega bar is equal to omega plus the nearest neighbors. Yeah, this is the omega bar. So if I want to just check the neighbors of x, not all the points in omega, then I call it the proximal subdifferential. And then furthermore, for fixed omega, yeah, I fix omega, then I define age of g, which is kind of like the definition of age, just the points p such that p times y minus x is bounded by whatever I have in my PDE. But I ask that only I ask that on the on all the sides or the edges of the boundary of omega. Okay, so this is kind of an omega adapted version of Wolf shape. Okay, so with these definitions, now I can replay like play again the proof of Cabret. Yeah, strategy one, the one that I referred to Cabret and Trudinger. Okay, so basically here I have to prove that age point A, I have to prove that age is contained in the total subdifferential of u. Yeah, so the sum of all possible p in this subdifferential, right? So you remember before it was the gradient of u in the continuum. I was having gradient of u applied to the contact set of u. So this was kind of the set of p such that I mean, in a continuum case, this was really the same as the subdifferential of u applied to omega, yeah, like here. And then just the convex geometry is nice enough that it allows you to interpolate, and even if you have a discrete set, it still works the same. So basically, if I want to prove why this inequality is true, why this inclusion hg is included in the union of subdifferential of u of x, then I just do the same proof. I say, well, take the minimum of the function u of x minus p dot x. If this minimum is on the boundary, then you get a contradiction from the right-hand side of your PDE of your boundary condition in the PDE and the definition of hg, right? So it's just the same as in the continuum, works this first inequality. Now the second inequality is because the interiors of the subdifferentials are meeting at this joint, right? So if I have two different subdifferentials for x and for point x and for another point y, then a point is in common to these subdifferentials if there is equality here. If ux is equal to uy plus p of x minus y, p dot x minus y, this is a condition implied by the fact that p is in common of subdifferential at x and subdifferential at y, and it means that p is in the boundary of the subdifferential. So it's just the interiors of this joint. And then if I look here, the proximal subdifferential is actually you impose an inequality for less values of z than for the subdifferential. So the proximal subdifferential is larger a priori than the whole subdifferential over omega. And now the point D is actually the clue, the point. So this kind of in the continuum case, this part was something like the integral of the determinant of gradient of the Hessian of u integrated over gamma u. Yeah, that was the place where, so this determinant of gradient of u is replaced by the volume of the subdifferential at x, and the integral is replaced by sum over x, if I try to imitate the continuum. And this is the place where I use the arithmetic geometric inequality. Okay, so this is kind of crucial. The main novelty of this work is maybe is this, the small novelty. So is that we here I define out this step of the inequality. I say that I choose Cx that is the optimal value so that this inequality holds. Yeah, and we are going to talk about this later. Okay, so suppose that I have Cx such that this is bounded by the Laplacian to the d. Yeah, like before I had integral over gamma u of Laplacian of u to the d, and then I had some other. It was divided by d. Yeah, I had some other factor. Okay, and this factor, kind of the factor d to the d. You remember this was coming in the when in the continuum case, I had d to the d appearing here. You see, it was kind of corresponding to the isoperimetric ratio of the Wolf shape, right? And then instead, in the discrete case, this d to the d is hidden in the definition of this constant c of x, right? So the c of x is kind of the whole property of the local geometry of my, so it's what matters about the local geometry of my graph and of my discrete setup for my chain of inequalities. Okay, so here was the d to the d was appearing here. Okay, and then let's go on with the proof. Then I bound here by the maximum product of Cx times the Laplacian. I bound by the maximum of all the Cx's times, well, here the Laplacian is bounded. I have my differential inequality. The Laplacian is bounded by this term here. So I just plug it in. It's bounded by that. Laplacian is smaller or equal than that. And then I just rewrite this sum, which is actually the boundary weighted by G. And I get, so you see, if I want to know what is my final isoperimetric inequality, I get that this maximum of Cx and this Hg are going to enter into the optimum constant. So the value of this Hg must have some geometric content, and the maximum of the Cx is, of course, has some geometric content, and they are the ones that govern the optimality or sharpness of my final inequality that I get. Yeah, so these are the steps, and then step D is the one that is the most interesting. I have my point X here, its neighbors, and these neighbors define to me kind of a proximal subdifferential, which is kind of it depends also on the function u. And then I have kind of, this is the volume of a polytope, and I have to bound it by something that has to do with this this Laplacian, which is a sum of ux minus uy times a weight for the again taken over the neighbors of my point x. Okay, so I have to think about this. So here I have decided to just say the main result before entering into this arithmetic geometric inequality, because I mean, in the end, this is the doubt of somebody who doesn't who just proved something and then doesn't know what is the best way to present it, right? So because how we reach the result is just that you try that all the steps work together and then rewrite the proof many times over until there is no gap in matching the extremes of the proof, right? So so maybe let me change my mind and talk to you about this subdifferential optimization problem first, because maybe it's easier. I could think that it's easier now. So now I'm looking at the problem similar to this one. So I'm just having in mind this inequality here. Let's study this inequality, this kind of inequality. Okay, and then let's forget about what is where U comes from and what is A. Let's forget for a moment, abstract this out, and then you end up with this kind of problem here. You have here is a hyperplane. The notion, the notation for a hyperplane. So I have a normal direction V, say, but not necessarily of norm 1, a direction V, and then I have a number C. And so this is a hyperplane. And now I find V, which you could think in the other case where I have X and I have my graph and there are all its neighbors, Y, Y1, Y2, and so on. And all these vectors form a set V, all these vectors from X to its neighbors, right? That would be where you apply this to. And here, I think that this would be corresponding to the subdifferential, proximal subdifferential of U at a point X, okay? Is some hyperplanes with normal equal to the direction towards my nearest neighbor, and I intersect all these. Pardon, sorry, it's half spaces, not hyperplanes. I just say hyperplanes a bunch of times. I'm sorry about that, but I meant half spaces. So I have an intersection of half spaces, which would give me a candidate for the optimum proximal subdifferential. And I try to find them. I fix, instead of having this incognito of this Laplacian of U at point X with weight A, I just say, well, actually what is this? This is just a sum of some weight multiplied by Uy minus Ux. And let's say that this is normalized out. I normalize to 1, yeah? So here, to find this optimum constant, finding the optimum constant in this inequality corresponds modulo dividing by, so supposing that this is equal to 1, I normalize, change the by a dilation so that my left-hand side is equal to 1, and then C is the maximum value that this left-hand side is equal to. Yeah, what is the maximum value of the left-hand side? This would be the C.
I'm sorry to interrupt you. We just have like 15 minutes talk, so you could maybe like have a few minutes more and just
stop. Okay, sure. And then
I'm sorry to interrupt you.
No, it's completely, you're right. So I'm sorry, because this is the first time that I give this talk, so I went over time. Anyway, so this problem here is very similar to the problem that Minkowski was studying when he was studying the, say, does it exist a polytope, a convex polytope with a given set of normals and a given set of facet sizes? So how Minkowski was studying the problem was saying, yeah, let me think about it as an optimization problem. So he was finding an optimization problem very close to this one, and found that if the normal vectors multiplied by the area of the facet sum to 0, then a polytope exists, and otherwise it doesn't exist. And so here is very similar. Here we have that an optimizer for this problem exists if and only if the span of this V is equal to RD. I mean, the vectors are in general position, and the sum of the vectors are 0. So the sum of the vectors are balanced. So an optimizer exists if and only if, and then the optimizer will be, if it exists, then also all its translations are also optimizers. This is not surprising if you think about the geometry of the problem, right? And then if you do Lagrange multipliers, then you find that the facet normal to a given vector will have area equal to this optimum constant times the length of the vector. In particular, you will have that the facet area is proportional to the length of the corresponding vector. With the coefficient, which depends on the choice of vectors that you fix yourself. And then, so we are looking for this kind of inequality with Cx all equal, and then we choose this Vx. If I have my neighbors, it's the best choice that that comes up is this y minus x, where y is a neighbor of x, times a squared. And then the optimal constant that for this inequality, the optimal constant is this CVX as in the abstract version of the theorem before. And the rescaled polytope. So here I have a polytope, and then I rescale it by the Laplacian. This will be this corresponds to the intersection of these hyperplanes, and the constants that correspond are the ones divided by the Laplacian of u. Okay, and so if I apply this this kind of version of this Minkowski related problem here, then I find that if the Cx is achieved at all points, and if all the Cx are equal, supposing that omega is connected, it means that, so you see, I have, if Cx is achieved, then f of x is proportional to the length of the vector from my Vx, which is this. So basically, I'm saying the area of each facet is proportional to the length of this vector, with a proportionality factor, which is depending only of x. So this is equal to this multiplied by a constant CVx, right? So in particular, this constant is the same for all y's. Yeah, so I have my point x. For all y's, I have the same proportionality constant between the facet of the subdifferential and the length of the vector. Well, but then this constant is also the same for the neighbor, for the relation for the neighbor subdifferential, and so on. So you get all the subdifferentials have the same proportionality constant. And then in the end, now I'm finished by telling you the result, which is let's start with this recipe, sufficient condition for equality. So recipe for finding a sharp inequality is that supposing that omega is connected, we just work on connected sets, and then the complex made. So if I have my graph restricted to omega plus the edges that form the boundary, the edge boundary of my omega, then this complex needs to be reciprocal to collection of I mean, points are dual to d-dimensional cells, and edges are dual to d-1 cells, which needs to be reciprocal, means that that's also the edge dual to a given face needs to be perpendicular, have direction perpendicular to it. Might be in a different position, but the direction needs to be perpendicular to the other direction. And so basically to this complex, to this one complex, so this graph needs to be dual the faces and facets of an equal volume Voronoi tessellation of a convex polyhedron H. And this convex polyhedron H in fact will be necessarily will be a multiple of this this one that I defined in the set in this in order to make the inequalities work, right? So I have a if I have a Voronoi tessellation, some of the tessellation is tessellating a convex polytope, then the tessellation has all equal volumes. Then what I can start doing is I define a graph that is dual to this tessellation, and then I use the second part. It's saying that the edge length divided by the volume of the facet needs to be constant. So now given this Voronoi and the reciprocal graph, I can define a squared such that this number is independent of the edge xy. And this gives me a way to fix a squared. And now that I fixed a squared, now I need to, then now it will happen that this hg here will be exactly the kind of dilation and translation equivalent to the Wolf shape. Okay, so this is the recipe. In the end, this is maybe the main point of this work is this: there is this recipe to start with a tessellation that includes convex polyhedra, and then start defining your Laplacian and defining your related graph so that you can find an optimal inequality in it. But this is not so far from being also necessary, because necessary condition will also need to have a face-to-face decomposition, and that your equality is achieved in the inequality. However, there is a problem that this hg in general, if I define it like that, you imagine you have your omega very complicated, and then you have your different normals. And then for each normal here, I find a different constraint that defines my hg. So in general, if the omega, if there is not some convex polyhedron inside your configuration of points, then you will end up with a hg which is much smaller, and then will not be able to find a sharp inequality. Anyway, so this is this. And the last thing which I want to mention is the relation to optimal transport. So the relation to optimal transport is this: if I have a point x, then I have the proximal subdifferential, and this actually the proximal subdifferential, right? So here it's RD, and here is another RD, where here is the space where my points live, x, and here is the space where my directions from subdifferentials that I call P are living. And so basically, if I think that these P's they need to have all the same volume, this is also following from this abstract theory, abstract description of the well, I'm going over time. So it's also coming from the abstract, from this part here, discussing the arithmetic geometric inequality. It also follows that all these cells are equal volume, and you can think of a transport that to each, here I put Dirac masses, and I move it to this to the image in the kind of dual space that forms a Voronoi tessellation. And in fact, the functions that achieve inequality, the equality in my chain of inequalities, are the kind of what is called Alexandrov solution to optimal transport, to the semi-discrete optimal transport between my points and the Wolf shape H. So the Wolf shape is kind of is divided in equal pieces, which are given by the proximal subdifferentials of pieces of my optimal function u. Yeah. Okay. So I just conclude with this. Here are many other connections which we didn't fully explore, but I stop here. Sorry for being a lot over time.
Thank you very much. It was a very nice talk. So please, questions and comments.
There is something in the chat. Ah, no, the slide. Yeah.
So at the beginning, I have a question.
Yeah.
So I wanted to understand. Okay, so you start with the continuous case, and then the first claim is that H is in this gradient applied to the contact set, right?
Yeah.
And then you get similar characterization in the discrete case.
Yes.
So can you? So is that all you can? So what else can you say about H? So you probably mentioned this, but I just didn't connect the things, just to make sure I understand. Right. So what can you say about this this optimal shape H?
Yeah.
Is it this entire right-hand side, or like what do you say about it?
But
right. So you have this. Yeah. So when you look at the first claim, for instance,
here
for the continuous case, or no.
In the
The first
case.
time you mentioned claim, yeah. So I can tell you the number.
Claim,
slide,
yeah.
Claim, yeah, is the keyword. Yeah. It's slide number.
Here it is.
Okay. Yes. Okay. Yeah. So, but what else do you know apart from this inclusion about H? So I just didn't follow.
I mean, so basically you have to, so here age was defined in a way here, my weight G, my G that I use in the continuum case is kind of different than in I mean, it's more restrictive than in the discrete case that I look at. And the G is defined, is the same for all the points, right? It's just giving you a weight on all the directions. And then the age is defined based on this G. And now what happens is that whenever I have a solution to this this PDE, whenever I have a solution to the PDE, the age is included in the set of gradients coming from the contact set, which in a way is what is basically the subdifferential of U.
Yeah. So H is effectively the solution of your isoperimetric problem, right?
So H is what is the dual to G in a way, the dual ball, the ball of the dual norm to G, if G would be a norm. G is almost a norm, it's just not symmetric. Otherwise it would be a norm. If G would be G of nu is equal to G of minus nu, then this would be a norm. So I look at the H, which is kind of the dual norm. And what I get here is that if I put this boundary condition, I just put this boundary condition to the PDE. It doesn't use the this part. It uses the boundary condition only, right? So if I have this boundary condition to the PDE, then age is included in the sub differential. Okay, so what it really uses the boundary condition only, right? It's saying, because if I have a point in the interior where the minimizer of this kind of function, if its minimizer is a point x in the interior, then automatically I will have that the gradient of u at that point is equal to p. Or if you are not so smooth, that it will be a point in the subdifferential, and you are done. So the only problem is that the point that you get a point in a boundary, right? That for some reason you end up with the minimum of this function being achieved in the boundary. And then in that case, you have that if I am in the boundary, I have a point x where it's achieved the minimum. It means that the function is growing towards the interior, and it is decreasing in the outer normal direction.
So okay. So what I'm trying to ask,
that here is the boundary of omega, and my u must be having a minimum here, and it must be decreasing here. So yeah, here is omega.
Yes. So what I'm trying to ask, I guess, let me try to phrase it better. So how much information do we really get about this isoperimetric shape, optimal isoperimetric H, right? From this inclusion. Other cases where you can actually identify.
So basically, there is a chain of inequalities. So starting here. So here you have a chain of inequalities, and this is true for all omega. All omega. Okay. And then all of the inequalities are true for all omega if u is a solution corresponding to this omega. Okay.
Okay.
And so in the end, you will so if you have, so the information about age is, you get that information if you start discussing when all the equalities are, or the inequalities become equalities. And then, so in the end here, you will have that I think u must be of the form x is like a parabola, looking almost like a parabola. Maybe there are other terms, but you really, here you see, in order to have equality, first you look here. What happens if you have equality? It means that d square u is equal to lambda times the identity. Yeah, if you have equality in the arithmetic geometric, then you have
yeah, all eigenvalues equal. Yep.
Is equal to, so it means that u is equal to lambda times x squared plus other lower order terms. And then in what happens? And then so you already have that. I mean, automatically you kind of have it's some kind of the magic of the problem is hiding the information, because it gives you that u is convex. So, and then you really find that now I know d square of u, and now what is completely determining my problem is that the value on the boundary of omega, the value of the gradient of u on the boundary of omega. And you need here, so let me remember. So I have that gamma of u needs to be equal to all of omega in order to have this other inequality, the equality. Okay, so in the end, I have the gamma of u. So the contact set must be all of omega. U, the Hessian must be lambda identity, and then in that case, h must be equal to the subdifferential.
Okay, and so you fully recover h when you have this equality. Okay, I see.
So I really fully recover. And then in the discrete case, of course, here just for the sake of, because sometimes you need a little bit more generality, because you want to, maybe you don't have, you can have a little bit more generality. But here you can imagine that if I define this h, then I just define it in such a way that I can find my contradiction and have this inclusion. Find the contradiction if the point where the minimum of the same of ux minus p dot x, I find the minimum of this. If it is a point on the boundary, I want a contradiction based on the left-hand side of my equation, and then of the boundary part of my equation, and then I am led directly to have this definition of h. And I didn't want to go further, but I mean, many cases where you can prove something are the cases where v is periodic, and when then g and a will also be periodic. So in a way, you would like to think that g is just the same. It just looks at the neighbors. At each point, they are the same kind of neighbors, and then you are you find that the candidate h, this hg, the candidate is always the same at all points. However, it can happen that this hg is not really so. I mean, if you look at the, I don't have any space. Maybe I just, let's see if my tablet, I can find something else to write. So if I have my triangular lattice, this is the problematic case. This was kind of problematic situation of the, imagine that I draw equilateral triangles, and then here the normal directions are like that, and the optimal, you can imagine that the optimal, and this is actually provable, but what we prove, that the optimal shape is a hexagon, and the normals to the hexagon are these. You see, they are rotated by 30 degrees. So the nearest neighbors will be all in that direction, but the faces have normals in that direction. So it is not always true that the edge that I define that way is going to be really the Wolf shape. But in, say, for this example of the triangular lattice, this is also backed up by the fact that I mean, we find the inequality. How do we find this? Where I do the sample results. I'm sorry for scrolling like that. It's annoying. Sorry, but so basically we find this sharp inequality basically by saying that this lattice, the triangular lattice, is dual to the honeycomb lattice in the sense of like say combinatorial geometric duality is dual to the honeycomb lattice. Then for the honeycomb lattice, we can apply the whole theory. So here for the honeycomb lattice, the possible directions of edges correspond to normal directions. They form this hexagon. So the optimal shape is a hexagon, and the normal directions to this hexagon are really realized by vectors of the of neighbors. So it's easy to apply our strategy to the honeycomb graph. And then so the honeycomb graph, and then this Voronoi tessellation that I was talking about is actually given by equilateral triangles. And then to pass from one graph to the dual graph, we use a lot of this elementary Euler characteristic and other invariants like that in order to count the relation between the edges and vertices in a piece of triangular graph and a piece of honeycomb graph. So it's very indirect, and then the inequality that you get is not the one we were aiming for. So if we aim for an inequality of more complicated shape, I don't know how to I mean, the PDE proof really has a left-hand side that is very close to this form here. So you really have like a boundary divided by cardinality. And this is natural in view of the divergence theorem if you want to it to be constant inside. And so you really, this PDE proof really can aim really, I don't know, maybe not, but most likely it can only aim at this inequality with a simple polynomial quotient of powers. There are cases like this triangular lattices where there are other polynomials in the cardinality of boundary and cardinality of omega, which I don't know how to reach by a PDE inspired proof. So that's so in that case, the Wolf shape that one guesses by this strategy is wrong.
Mm-hmm.
I mean, it's wrong. Is not, doesn't show you optimality or
the
equality.
solution. Yes, yeah. Okay.
So that's an interesting thing to think more about, because it's not. Yeah. I mean, I have to. So there are many results, many more links there, because every time you talk about Voronoi tessellations or convex functions, then there are many connected ways to talk about the same thing, and it is not clear that the one that we ended up with is the interesting one, the most successful one, but at least it allows to give some examples.
Thank you very much. Maybe more questions or comments?
There are not many people left.
We usually have 50 minutes talk, maybe it's but it was very nice talk, so thank you very much once again. Maybe we can stop.
Yeah, thank you.